Hey, hi there. So welcome to this session on UVM sequence item, sequence, sequencer and driver. So main agenda of this session will be how these various things interact together. We have not formally looked at how the sequences are created, what are the different types of sequences we can create, and how does the sequencer behaves, what exactly does it do. So we will look at those details and various forms of the interaction protocols that are allowed, and then we will also look at in the context of that interaction how the sequence item port that we had discussed in the context of TLM gets utilized. So we will look at those as well. So let's quickly jump into the agenda of this deep dive session. So our agenda would be that we will start off on how to model a transaction with the UVM sequence item. We will look at that, and then we will look at like the bit of introduction about sequence, sequencer, and driver. These three components interact with each other, so we need to look at that interaction and understand it. This is an important concept that you guys need to know. And then we will go into different models of interaction that are possible. So we'll look at unidirectional interaction, then bidirectional interaction. In the bidirectional itself, there are flavors. How do we do that? And then bidirectional without pipelining and with pipelining, how to do it, right? So for all these three ways, how do we model the communication? And while we model this communication, it's actually the sequence item port that gets used. So how the APIs are structured around it to make that communication among them possible. So we look at it in detail, and then we look at different flavors in which we can write sequence. So how to write simple sequence is something that we have seen a few flavors as a part of our bootstrapping session on UR test bench. Then we look at how to build nested sequences, and then how to do the parallel sequence. This also we have seen to some extent with the help of virtual sequence in the context of UR test bench. Then we look at a very briefly, so reactive sequence, we'll look at it very briefly, and then we look at like briefly at a layered sequence. These are slightly advanced topics, and then we'll understand a little bit more detail of virtual sequence. This is another important concept which we have already used it, but we will formally define it and understand it further, and then we'll close it with the virtual sequencer. So this is the agenda for this deep dive session. For the UVM sequence item as well as sequence, we'll be primarily exploring the object hierarchy. We have been very closely exploring various things about component hierarchy, but we haven't explored much about the the object hierarchy. So we will be doing that as a part of this session. So let's quickly refresh that. So we have UVM object, and UVM transaction extends the UVM object, and then we have UVM sequence item which extends UVM transaction, and then we have UVM sequence which extends the UVM sequence item. And UVM transactions when are the actually the building blocks of communication between the components of the UVM test bench. We had looked at the TLM concept. So through the TLM we communicate the transactions, and they are used for all purpose, right? Even your stimulus generation is done with the help of transaction. Your monitors the interface and creates a transaction, and they get consumed either in the scoreboard for checking or in the coverage monitor for capturing the functional coverage. So this way, for this entire process of coverage driven constraint random verification heavily relies on the concept of transaction. Even during the core concept, we had understood how transaction transactor philosophy is sort of fundamental to building the object oriented test benches. So UVM transaction, so now when I'm talking about it, so often whenever we use this term transaction, it might be tempting to correlate to UVM transaction base class. So UVM transaction is typically not used for modeling the transactions. It's actually the UVM sequence item. This is the one that's used for modeling the transactions, and that is because the UVM sequence class, which ultimately generates the sequence items, or what we would like to call it as transactions, it generates in terms of UVM sequence item base class, not in terms of UVM transaction, and UVM sequence is our primary vehicle for generating the stimulus in the UVM test bench, and that generates UVM sequence item. So now on, whenever we say like a transaction or a UVM transaction, we are going to refer to UVM sequence item and not to UVM transaction. That is something that you need to keep in mind. Now comes to, like, for example, how do we, like, what should we be putting it in the UVM sequence item, right? So those are the questions. And then what does UVM provide built in, and then what do we need to do with those as a user? So those are some things that we will explore as a part of this session as we go forward. So what should be the part of sequence item? Anything that is related to your high level stimulus should be randomized as a part of your sequence item. Yeah, there might be a question that do you need to add all the signals that are present in your interface to the sequence item? The answer is no. You don't have to by default add all the signals that are present in your interface to the sequence item. You don't have to do that. It will be like sometimes you might add a few of the information that you have extracted from the signal or to be driven to the signal as a part of the sequence item, but blindly you should not be thinking of adding all the signals that are present in the interface that's either being driven or being monitored. You don't have to make it a part of the UVM sequence item. So that's something that it's not by default. So that's something that you might want to remember. And then there is another thing that the UVM sequence item, especially when you have a protocol, like for example, when we saw the APB, right, wherein we can send a request and we can also receive a response, right? Where response was the data that was being read. When you have the response, now what the sequence item, the way we can use sequence item is such that we can put even the response information as a part of the sequence item. So it can contain fields related to your request as well as the fields related to your response. Okay. Now when we do that, right, when we do that, you should take care to randomize only the request fields, right? You should not randomize the response field. So typically we will have the habit that whatever the fields that we declare within the sequence item, we will be like, prefixing them with the rand keyword. Don't do it, because every time you declare extra the fields with the rand, you might say that, yeah, let it get randomized anyway, I'll overwrite it with what I observe on the line in the monitor. But the problem is that whenever you do that, whenever the object gets randomized unnecessarily, the constraint solver will get loaded to solve the constraints for them. And obviously if you are not going to use the value, you don't want to unnecessarily randomize and reduce your simulation performance. So overall, in summary, you don't need to add all the signals of interface. On the need basis, you might add the values required for few signals that might have to be driven, or few control signals that you might have to pass it on for the high level checking or for biasing the stimulus that is being generated. Like let's say for a FIFO, if sometimes I might want to pass the full information up so that I can stop the generator, right? Let's say I want to do that. But for example, let's say I have a ready valid interface, right? So in the APB, I don't need to really model ready valid as a part of the APB sequence item, right? So that is the point that I'm trying to make essentially over here. And then the response or any state type of information, if you are planning to put it in your transaction for the local usage while randomization, then just take care not to randomize it. So these are a few things. Now let's move further as to what does it exactly, what is the UVM providing as a part of UVM sequence item, and how can we use it to model the transaction further. So when we say modeling a transaction, what do we really mean is that the way we implement the transaction should ultimately satisfy all its use cases. So let's understand from a test bench point of view what are the different use cases that we may have. So the way overall, as we have seen, the UVM sequence is our primary vehicle for stimulus generation, and UVM sequence generates bunch of sequence items. So test starts the sequence, we say sequence.start, and if it is a simple sequence, we pass the sequencer, and then the sequence generates series of randomized transactions in the form of sequence item, by when it is run on the sequencer, and then sequencer sends the generated transactions to the driver. And what the driver does is it does something called packing, right? And packing is not mandatory action that's applicable for all the types of transactions, but there are certain protocols in which what happens is you send various fields, randomized fields, and when they are sent on the bus, right, those fields are sort of packed together. Packed together means organized in certain order, and then they are sent from, like, let's say LSB onwards in the form of, like, let's say 4 bytes each in some way, right? This especially happens for, like, the serial protocols, right? Many of these serial protocols, you do the packing of various fields together. We'll look at an example, but that can optionally happen as a part of your driver. So driver takes that transaction, optionally packs all the fields, and then drives it onto the interface. So that is one requirement. So I might have to pack all the fields. If you don't understand what is packed, don't worry about it. When we get with an example, it will become clear, but just register the term that we might have to pack the fields. So second point is, like, checking and coverage. So monitor will look at the interface, and then what it will do is it will capture the various the various signals, and that information could be in a packed form, because typically when you send information on a hardware, right? So if you remember our packed array and unpacked array concept, so in a packed array we will put all those information together, right? And in the unpacked type of an array, or especially when we did the like a union type of a concept, or a packed struct type of a concept, we were able to compress all those fields and create a bit vector out of it, right? So you will remember that idea, right? So, and then that like the bit vector that we created could be stored in a particular memory location or something, and then when you read that bit vector back, you can put it to that pack struct and then look at it as fields, right? Like, okay, this field is a instruction type, this is the operand 1, this is the operand 2, but when it is put into the memory, it's just a 32-bit instruction. So like, separating it out into different fields is an unpacking operation, and combining all fields to create one of those vector is the packing operation. So when the it's not, as I said, it may not be applicable to all the situations, but it is applicable to a lot of such real hardware situations where you are storing or where you're transmitting some information. This pack and unpack is present. Hardware generally consumes it in a packed form, but when we process that information, we unpack it because there is something meaningful contained. It's not just the ones and zeros. Those ones and zeros mean something, right? But the hardware consumes it as just the ones and zeros, or at least when we communicate to hardware, we just communicate in the form of some bit vector numbers. But when we really want to process it in test bench, we want to segregate it into different fields. So a monitor could be monitoring a bus where it might be picking up an entire instruction, and then it is unpacks it. It says this is the instruction type, these are the operand 1, these are the operand 2. That is called as unpacking. So the transaction might have to model the unpack, right? So that is what is required. And then transactions are shared to analysis components, and sometimes the coverage and scoreboard type of analysis components might want to make a copy of it to store it for a while, and then they might synchronize it with some other activity to figure out whether something has passed or some particular scenario has taken place. So we might want to do the copy, right? And the copy, as we know, the system Verilog only supports the shallow copy, and typically what we want is we want a deep copy. That is, all the fields, any hierarchies, any objects present, we would like them to be copied completely. So that is something that's accomplished with the help of the the copy functionality. So copy functionality, we would like to have the deep copy support. And then in the scoreboard, what might happen is we might get one type of transaction, we might store it, and it might get routed to another port or something like that, and the same transaction might be coming out. We want to take that particular transaction, now that transaction becomes an actual transaction, and we want to compare these two, right? And it's the same transaction types, and we want to compare these two and figure out whether they are matching or not. So this is another operation that we would like to be modeled as the part of the transaction. So these are various use cases that transaction modeling must support. So let's put what we discussed in the previous slide in some perspective with the help of a picture. So we have, like, let's say some XBus transaction which is extending UVM sequence item, and it's registering to the factory using the object utils because it's a part of object hierarchy. And then we have bunch of properties which are part of the request and that have been declared as rand. And then when we send it out on a bus, let's say we send out all these properties on a 32-bit bus, and this is the way in which we order them, pack them, right? So there's the pack, and then we send it out on a 32-bit bus. So that is the sort of concept of pack. And then let's say we have the, for debugging, we are putting the string device name, that we are not declaring it as a rand, so it's an internal debug variable. And then let's say 1-bit response comes in. This is just a imaginary transaction, so 1-bit response, and that response we are not randomizing. Then if we were to use this transaction in this type of an UVM test bench, where what are the additional methods and where do they get utilized? So let's quickly look at it. So in the scoreboards and the subscribers, and we have, so in the subscriber, let's start with the subscriber. So in the subscriber, we might want to do the copy, right? So as we talked about, and the way we will call it is whatever the transaction handle dot copy, and then pass it to another object handle wherein we would like to copy the fields. Okay, so this is one use case. And then we would like to do the transaction.compare that will happen in the scoreboard. So these are the methods that we would need. And the when we run the sequence on the sequencer through these sequence item port, the sequence items will be sent which are created by the sequence, and the driver would drive it. And before driving this 32-bit data, let's say it drives it out on the bus, it will pack them and drive it, right? So these are the various fields. It is packing it in this order and driving it. And so before doing that, it is going to call tr.pack. Okay, and then similarly when we have the on the monitor, when we receive the 32-bit bus, let's say I want to unpack it, right? So then I can call tr.unpack. Okay, and then those fields will be get spread out to the individual fields. Okay, so that's what I can do. And then we have the we looked at the compare, we looked at copy, we looked at pack, and we looked at the unpack. And then we have few more functions. So we have so these are the functions, by the way, which are part of the UVM sequence item, and I was just showing which components in the test bench utilize those methods. So you have a method called doCopy that's provided as a virtual function as a part of our UVM sequence item, and the way this gets invoked is through a function called copy. So whenever you call copy, internally it would invoke doCopy, and that is what is user is expected to populate. And what exactly needs to be done over here, we will look at it. Similarly, when the user calls compare, internally the do compare gets invoked, what needs to be done over there. So these are the placeholder functions which are present as the part of UVM sequence item base class. What we need to do with them, we will look at it when we go to the implementation. So we briefly talked about copy, compare, pack, unpack. We didn't talk about convert to string. So convert to string converts all these fields in a form of a string that can be printed for some debug purpose. And then do print will actually print all the fields. And then there is a concept called do record, wherein the fields of the transaction can be either posted to a file or can be posted to a database. So that's the another feature that's present as the part of the UVM. So now in the next few slides we will look at how to populate these functions and what exactly we need to do. But in summary, these are the functions that are already present as a virtual functions as a part of UVM sequence item, and they get invoked through the version that is without do underscore. So do underscore copy gets invoked only with copy, do underscore compare gets invoked only with the compare, so on and so forth, right? So except this convert to string gets called as is, but rest of them they get invoked without having to use the do underscore and then the remaining whatever the suffix string that is remaining. That's how you invoke them on a transaction, and internally within the transaction the corresponding do underscore copy gets invoked. So let's look at how to use these functions in the next few slides. So some documentation about it from the our UVM base class reference guide. So UVM sequence item, this is the base class for user defined sequence item, and also the base class for UVM sequence class. This was what was the important point that we are making, that the UVM sequence item generates the UVM sequence generates the UVM sequence item. That's why any transaction we need to model it with the sequence item. This is the hierarchy so far. We have the void, object, transaction, and then the UVM sequence item. And then these are the bunch of functionalities that is present within the sequence item. But I think like there are like the key modeling functions that we were talking about. They are actually part of UVM object, which is extended from the UVM sequence item. So these are the function definitions that we talked about. So you will have a do record, and then the record is the function that the actually gets called. Similarly, you have do copy, and then the copy is the function that actually gets called with the object, so on and so forth. I'm not showing all of it, but you know, this functions, the modeling, the transaction modeling key functions that we talked about in the previous slide are actually part of the UVM object, and through the extension hierarchy they are available even in the UVM sequence item. There's one function called set ID info. We are going to be looking at it. So this function, it copies the you know, the sequence ID and transaction ID from the referenced item into the calling item, and the routine should always be used by drivers to initialize response for the future compatibility. So this is something that we will be using when we do the when we start going into the implementation of the driver. So I just wanted to seed that thought, but I think primarily I just wanted to showcase the documentation part a bit, and then main thing I wanted to highlight was that these functions that we saw in the previous slide are actually present within the UVM object base class, because we are going to be looking at the implementation of these in the next few slides. Okay, this is the bit of documentation snippet for the UVM sequence. So this is the overall hierarchy for the UVM sequence. So it's actually, we have a UVM sequence item, then you have a UVM sequence base, and from that we have deriving the UVM sequence parameterized by the request and the response type of the transactions. And then I'm just showing you a few snippets of the methods over here. I think the key methods like the start and the body, they are present as a part of the sequence base, and then the get response itself is present as the part of UVM sequence. So let's just quickly look at it. So body, this is the user defined task where the main sequence code resides. So we have looked at few of these sequence examples, and we have seen that like the UVM sequence actually generates a stream of you know, the sequence items or other sequences. So that whatever it generates is put in the part of this virtual task body, and this is the definition for it. And this method should not be directly called by the user. So the user should be creating a object instance of the UVM sequence and should be calling dot start on that particular sequence object. And when you do that, you have to pass the sequencer. You can pass the parent sequence if you have doing a nested sequence, and then you have the ability to enable the pre and the post type of body functions, or a pre-body and post-body functions that can be enabled, that can be called similar to the randomization, right? So you know that there are pre-body and post-body that can potentially tune your sequence, and then you can also specify the priority of the sequence. Is useful when you're running multiple sequence parallel on a single sequencer. Then you can specify the priority is based on a number. We will look at one of these examples as we go further. I just wanted you guys to feel that okay, this is all there present in the documentation, because while we start building examples and we look at those examples as a part of this series, we might not like sometime realize that, oh, from where is it coming, right? So that's why I'm showing you a few things. And then we have the get response function that is available within the UVM sequence that we will be utilizing, and then it takes in, for example, what is a response that we are receiving, plus it takes the transaction ID. So if we specify a transaction ID, valid transaction ID, then it will wait for it. So what generally happens is when the sequence item, like a request sequence item, passes through the sequencer, it stamps it with the like something called sequence ID and transaction ID, and when the in the driver when it processes that particular request and it creates a response corresponding to that particular request, whatever the IDs, the sequence ID and the transaction ID that the sequencer had stamped in the request must be extracted and must be stamped into the corresponding response object if we are creating it as a separate object. Okay, so this concept we will look at it, but just wanted to show you, since we were looking at the definition of some of these functions, that so the driver has to stamp it, and then if the driver stamps it, then when we say the get response, we can we can say get response in the sequence, saying that get response to this particular ID, right? So we can do that. So in the sequence item, we saw that there was another function called set ID info. So when the request is received from the driver, then it can extract those parameters, and then extract means it can create a response object, and for the response object it can say set ID info and pass the request item that it has received, right? And then that ID information would be now stamped to the response, and when the driver sends it back to the sequencer, then the sequencer can use that information to route it to the appropriate sequence. And if within that sequence, because this get response is the function, get response is the task of a particular this is the virtual task of that particular sequence, it can match and receive the appropriate the response, right? So this way, or it will just receive, if you don't specify it, whatever the order the responses are coming in, it will receive. So you can match automatically match the request to response using this ID mechanism that exists within the part of the UVM sequence. So we'll be looking at some of these functionalities, but what I wanted to, some of the core functionality that gets frequently used, we will definitely be describing them, but there's many more features that are available, and by showing you these snippets of documentation, I encourage you that when you start practicing, keep taking a look at these to learn more about it. So we have looked at that we are going to be using UVM sequence item for building the transaction, and then we looked at the bunch of functionalities that we would need for it to be used for stimulus generation, for checking, and for the functional coverage. And now we found out that those virtual functions are provided as a part of UVM object which the sequence item is deriving. Now those are just virtual functions, right? How exactly to use it, how exactly to implement it, we will look at few examples to gain some clarity in it. So let's start off with the do copy. So I am showing one of the transactions with which we had started off. Let's say this XBus transaction extends UVM sequence item. I'm not showing the fields to just save some space, but then we say function void do copy UVM object RHS. This is the standard declaration, and we use this as is. And then what we do is we create XBus transaction for the right hand side object, and then whatever the, so you notice that the RHS is what is coming in, because that's what we are trying to copy, right? So the RHS is what is coming in, that's what we are trying to copy it into the sort of the the LHS type of an representation. So this is like it's going to be A copy B, wherein the B gets copied to A, right? So that's the idea. So notice that these two handles are different. The RHS is the object that we are getting, which we want to copy, and then this is internally we are declaring the RHS underscore handle. But note that this RHS underscore handle is of the type of the final transaction that we have created in the test bench, whereas the one coming through the function, so the function doesn't know, right? So it's just a part of the UVM object, so it's a part of UVM object RHS, right? And this all happens through the concept of polymorphism, right? So because these are all virtual functions, it would still work, but before doing that we need to sort of cast it and check. So first step we are going to check is that we will do the dollar cast of RHS underscore to RHS to see whether both the objects are of the compatible type, right? And if they are compatible, then we call the super.doCopy. There can be multiple levels in which sometime the transaction could be implemented. Even if it is not, they still need to call the super.doCopy to call the anything related with the UVM itself has few fields, right? So they need to be copied again. So you call the super.doCopy and pass the RHS, whatever the argument that you had received. But okay, this is all sort of like, you can think of it as boilerplate. Boilerplate meaning something that will repeat in every transactions do copy implementation. The only difference being you would be declaring your own transaction handle over here and doing the cast based check, but the subsequent code is going to be dependent on the properties that are present within your own transactions, right? Those are the ones that you need to copy. So you're going to say like we had this address, transaction type, size, byte enable, device name, response. So these were the fields that we had declared as a part of our XBus transaction. Now what we are going to do is we are simply going to copy the corresponding properties from the RHS underscore handle, because after the cast we would have assigned it to the RHS underscore handle. So from that derived class handle we are going to access those properties and copy it to the current class, right? So that's all that we really need to do. And if there are any objects present, the object handles present, then you can keep on calling the do copy for those object handles as well, similar to what we have done with the super.doCopy. If there are object handles present as properties within the class, you can call the corresponding doCopy functions to continue with the deep copy process. And the usage is something like this. So you'll have XBus transaction, which is your data type. We are saying A comma B, we are declaring two object handles, and assume that in a we have assume that in a B we have a proper object, and that we want to copy it to the object that's present in A. Then we just say A dot copy B, and then what will happen is whatever is the content of B will get copied to A, and that happens through this process. Or there is another way you can do, which is you can use, like there is a clone function that also you can utilize, that will return the object B, and then that can be that will create a copy, right? That will create another object of B, and it will do a deep copy, and then that object it will return that you can assign it to A using the dollar cast, right? So that also you can do. So in both the ways you can implement the copy functionality. So we looked at already the how to do the do copy implementation and how to invoke it in two different ways. We looked at it. So we'll now continue to look at other functions. So we have again our XBus transaction extending UVM sequence item, and then we have the function bit do compare. It has a return type called bit do compare. It will return true or false depending on whether the comparison has passed or failed. And again we have this argument is same UVM object RHS, but we have one more additional argument called UVM comparer, and then we have created one more argument name called comparer. This is called as a policy class. So policy class, you can use it for if you are building some advanced things, Advanced things meaning, like for example, when there is a mismatch takes place, how the mismatch should be handled, like up to few fields are mismatching, how it needs to be dealt. So there are various ways in which such team level policies can be defined, but I think for our current basic understanding we can ignore the policy implementation. It's a sort of an advanced concept where where some teams want to mandate something or want to enforce things at much higher level to standardize something, is where the concept of policies comes into play. So for now I would recommend that you don't worry about it. Let's focus on the core part of it. So we have UVM object RHS, which is what we are trying to compare. So what it means is, let's say we have X bus transaction A comma B. Please note that I'm not showing you how these objects have gotten created, but understand that at the point in the line 336 these two objects are present. Okay, so that is sort of like that's assumed. So I am now doing a dot compare B, right? So now both of these objects are going to be compared. Of course, in order for the line 336 to execute correctly, both the objects must be present. If the objects are not present, then it will obviously result in null reference access, but I'm not showing you that part of the code because our primary focus is to understand how the compare functionality works. So here we are assuming that both the A and B objects are present, and the way you use it is you say if A dot compare B, and the B would map to the RHS over here, and our function will return true or false. And when you do this, the do copy function that's present within this sequence item A would get invoked, and the sequence the B would be passed as an argument over here as a RHS. This boilerplate code that we talked about remains same. So we declare RHS underscore, we cast whatever the incoming object to see if it matches the extended transaction type that we are trying to compare. If it is not, then we already return 0, saying that it is already failed. Else we are doing it in one line, but you can obviously write more code to make it simpler looking as well. So we call super.doCompare RHS and comparer. This policy object you can just keep passing as it is whatever you have received. And what additionally we are doing over here is we are doing the logical and we are now putting the comparison on each of the fields. That is the current object's address, which in this case will be A object's address, whether is equal to RHS underscore dot address, which will be the B object, which we have casted and assigned it into the handle RHS underscore. So then transaction type again for the A is equal to RHS underscore dot transaction type, which is B. So on and so forth for each of the individual fields. We are comparing and then ANDing them together, so that if any one of these comparison fails or any of the fields in the base class field comparison fails, then it would return false. But if everything matches, then it will return true, and then your if will become true, and then you can take further action. You could be using, let's say, UVM info saying that things are matching, or you could be using UVM error or fatal to indicate tick UVM error or tick UVM fatal to indicate that the comparison has failed. Okay, let's move on to the next function that's present as a part of modeling transaction, and that is convert to string. And convert to string is a function that's generally useful for logging the debugging information. It returns the string data type, and typically this is the placeholder function that would be provided. And within the transaction, what you typically do is you declare a string, and then you say like super.convert to string, so that any base class related information can be obtained. And then you use this system task $s format, and you pass the string, and then along with whatever the string value that we have gotten in the s, we add other properties of this class that we want to make it a part of the string. And here the format specifier string, typically whatever we use with the even the $display or $write, the system task, the same format specifier can be used. So we are using like a %h for the hex values, and then %s for string, and we have %b for the binary type of values. So on and so forth. You can look up the various format specifiers available in the LRM, but for the different data type, different format specifiers are available. The width of the data value that is displayed can be controlled as well. That's also something that you can explore. So using those, what you essentially do is you specify within this particular string, you create the string of all the properties that are present, and then you return that, right? Because we have returning the string, and the way it gets used is whenever you are trying to display something, then you can say a dot convert to string. The like why one needs to do this compared to like do print, which we are going to see in the next slide, is that sometimes you want to like combine this information with some other information, right? So like for example here, I am displaying some information, right, like express transaction A or something, but this is just a very simple example, but there can be like other information that I want to collect together and also display this transaction information. In those cases, like the convert to string type of a function is very useful. And just like to reiterate that it will use the typically you can use the $s format function within the convert to string to create the string. We looked at the convert to string. Let's look at next function, which is a part of modeling the transaction, and that is do print returns nothing, and it takes this argument called UVM printer with the handle name printer, again part of the transaction class extended from the UVM sequence item. The function itself is provided by the object and becomes part of sequence item through the hierarchy of extensions. And what the idea is that the printer is a class that actually provides an interface for printing UVM objects in various formats. And this is the quick documentation snippet from UVM base class library. You can always Google UVM underscore printer and it will show up the documentation, right? So multiple sites host the UVM HTML documentation that comes up, so you can browse this information. And as well, it's part of the UVM the package or the zip file that gets delivered when you download the full UVM, so that you can have the local reference as well. So the idea is that the UVM printer is a base class to which you can add all your fields that needs to be printed, and then you can assign like how it should be printed, right? So there are some built-in formats that are supported. You could print it in a form of table or a tree or a single line, right? So there some of them are built in. You can create a custom the printing format as well. That's why these are also called as like policy objects, right? You can see that here. So these are called policy objects, so that if some team wants to print it in certain format, then they can define their own the extension of printer and can assign it. But within the within the do print function, you just add the fields, and then the default printer that needs to be used can be set, and through the default printer. So for we are not going to change anything. The default printer is typically set to the table printer. So what we are going to do is we are going to keep it simple. So we will just add the field. So this printer class provides this bunch of functions to add the different type of fields. So here I am using just the print field and print string type of functions. So like I've just put like how the print field works. So you have print field and it takes a string name and then the value, the size of it, right? So those are the three critical parameters that we specify. You can of course control radix. There's a scope separator, there is a type name that you can specify. Of course, we are going to do the simple implementation over here. So we will say printer, print field, and when we say address, which is a name that we would like it to appear when it prints, then the variable, and then the number of bits in address for which we are going to use the system function $bits. And then if you have the string, then you say tr type, and then since it's a enum type, tr type dot name, when you call it returns the string value for the current value that's present in the tr type variable, and then tr size is another variable, again with the dollar bits we can specify the size of it, and then we have the the string device name. We just adding the device name, and the device name variable itself was a string, so we are directly adding it. And the response was a 1-bit field, so here we are adding response is the name that we want it to appear, and then we are saying the name of the variable and the number of bits in it is 1. So once you add this, the default printer would already be set to the table printer. So whenever you have a valid object in, like let's say we declare the bus item A, and then we create the we call it as a dot print, and then when we call the a dot print, it will print it in the tabular format as shown over here. Of course, I am showing a print of some other transaction that was available. This I have taken it from the documentation, but when you run it, it will appear in the similar type of a format. It will be able to show you the name, the type, and then the size of it, and then the value of it, right? So in the similar format it can be printed, and as I said, if you want a different format, you can change it to whatever you desire. So we'll look at a couple more transaction modeling functions, and they are pack and unpack. So before we jump into the pack unpack function, I just wanted to quickly talk about the policy class. And these are policy classes, are the arguments that we have been seeing. Like for example, UVM with the do print function, we saw that we had the UVM printer. So similarly, we have UVM packer, and UVM packer is a class that provides the policy object for packing and unpacking the UVM objects, and the policies determine how the packing or unpacking should be done. And packing an object, what it does is it causes the object to be placed into bit, right? Or you have the you have the ability to put them in byte or int array as well. Now to do this, like for example, now what the idea is that you like in this concept will remain same, right? So you have these policy objects and you pass all the fields to the policy object, and then the policy object will have the ability to do the required functionality with different possible policies, right? So for example, here the policy could be that I want to pack all of them in bits, right? So I want to put them in one long bit stream. That is the way I want it, right? So that's the default one. Or I want to put them together, but I want when I want to use it, I want to use them as a byte array. Let's say I have a byte wide interface and I have these multiple fields. I want to pack them in a form of byte array and send them byte by byte to the other side, right? So that also is possible. Like for example, I might have a UART, and in UART I am communicating at a byte granularity, right? So if I'm communicating at a byte granularity, but I am communicating certain packet format on that UART communication, and that packet format contain several fields. Like for example, the one bus transaction that we have been seeing is a 32 bits. So what I can do, I can pack them in a form of 4 bytes and take each of the byte and transmit it over UART to the other end, and the other end receives it, and then it can unpack it into fields and use those fields to do some processing, right? So that is the idea. And now the policy is that the packing could be done in bit, or packing could be done in byte, or packing could be done in int. Once you have added the fields and told what is the size of those fields, then you can utilize the the UVM packer object to pack them in different formats, right? So that is the variation. And then there is a concept of endianness, like little endian, big endian. So there are so many variations that are possible, and all those variations can be managed with the help of this policy object. That is the fundamental idea. And so what happens is that these objects provide two things, right? One is we need to pass the input about what are the fields that we want to pack or unpack, and second is in what format do we want them packed or unpacked, right? So those are the two things. So first thing, to provide the values to these functions, these various policy functions, there are two ways. One is I can provide the fields individually to the individual policy function. That's what we have been doing, right? Like for example, in each of these transaction modeling functions, we are doing it in different ways, and that's intentional to show the variations possible. For example, with the UVM comparer, we didn't even use it. We just did the comparison by ourselves, right? So that is one thing that we did. And second thing is, with the UVM printer, we made sure that we use the macros. We use the direct, we use the direct UVM printer and invoked its function. That is another way to do it. There is a third way that wherein it provides certain macros, and those macros internally again operate on the that particular the functions or the properties, the methods or properties provided by the policy function. That's the third way. There's a fourth way that there's a concept called field macros. I am not going to be, we are not going to be looking at it because it has its own some limitations, although they look very attractive. So but there exists a concept, so I want you guys to sort of know about it, that there exists a concept called field macros. So you can define field macros, and once you define field macros, so using these field macros are kind of connected to all the policy object, like the printer policy object, pack, unpack, all of them, right? The compare policy object, and they can push whatever the field that you have commonly defined to all these policy objects, and hence you can get all those functions, right, automatically populated, right? I can get automatically do pack, do unpack, do compare, and then do print, all of them once I define field macros. Because ultimately, if you look at it from a big picture point of view, in all these functions we are providing our fields, right, and then they are doing some simple operation on those fields. So what UVM has done is that if you want to populate all of them, you just define field macros on all your fields, and then it will automatically take care to generate those functions for you. So that is the idea of the field macros, but it comes with its own limitations when you have more complicated things to do. As and when you automate more and more, you tend to lose more and more control, and this is not such a big thing to do. So when you do it with the field macros, you get some coding gain, but the loss of control sometimes is sort of like not very justified when you are doing the when you are doing a more complex projects. So in the UVM packer, for example, now we have this pack field type of a function. So I could be calling UVM packer.pack field and pass my field, right? That's the input I need to pass. That's one way I could be doing. Or I have these macros that directly deal with the UVM packer, right? So I can call this tick UVM pack int n, right? So I can pack this, like for example, integer field in it, and like for example, let's correlate all of them. So I have a pack field int, right? So this is the function. So I can be calling UVM packer.pack field int the way we did it with the UVM printer, or I could be calling, for example, I have a macro called tick UVM pack int, right? And I can just pass the variable. That's another way of doing it. And I am just showing you internally over here that it calls again tick UVM pack int n. This is the code documentation that I'm showing, and in the int n, what it does is it again goes into the packer. If you look at it, it again goes into the packer and adds some things to the embeds. And if you now open the functionality that is present in the pack field int, it will look similar to this. So the point is that there are multiple different ways of doing same things. Everything has small advantages, disadvantages, as we call like a 1920, right? So a small is not a big difference between them, but there are multiple ways of doing things. So from your point of view, what is important is you understand what is the concept that we are trying to do over here, that we are trying to model a transaction. As a transaction modeling, what are the different functionalities that we need to implement, right? Like we need to implement print, we need to have convert to string, we need to have pack, unpack, right? We need to have compare, we need to have copy. So understand that these are the functionalities that we need, and the ways to implement these functionalities in UVM, there are multiple ways, and at least know one of the way or one of the pattern that we have been showing, and then other patterns you can explore as you start implementing and using it in the future. So that is the basic idea that I wanted to see. We had not talked about it, but before we closed on to the last one, I wanted you to know why are we seeing a lot of variations. I'm just showing you different possibilities in each of these functions. So we will look at in this one, we will not directly use the pack field function in the packer, but we'll try to use these macros and build the same solution. All of them again lead to the same thing, like all rivers go to C. So same thing, I mean the functionally they accomplish the same objective. Okay, so before we jump into the implementation of the pack and unpack, let's quickly understand what is it that, like in a real life, how does it really translate to, right? So let's say I'm taking a PCIe packet. So PCIe is made up of 3 layers. Okay, don't worry too much about the details, just sort of try to understand the gist of it. So 3 layers, you would have of course studied the OSI layering model as a part of your coursework. Most of you would have studied in networking. So the PCIe contains 3 layers, right? So, and what happens is whenever I want to transmit any data, each of the layers adds its own stuff, right? So it adds its own stuff to accomplish its job, right? So like multiple logical stream multiplexing is the, let's say, the job of transaction layer. The data link layer says that if I take a packet, I'll ensure that it gets communicated reliably to the next hop, right? That's the link layer's responsibility, right? And physical layer will make sure that it is get converted to serial streams and communicated at a particular speed, and it will ensure that the symbol and the bits are recognized correctly. The distinction is being made at the other end, right? So that's a responsibility of the physical layer, such that like the data can be recovered and both the bit and the symbol can be recognized, right? So that's the responsibility of the physical layer. Now in order for each of these layers to fulfill their responsibilities, they need to add something to the packet that needs to be passed on to the other end. So that is the basic idea. Now now all that detail I just told you for you guys to understand, but what that really matters is this. Okay, so I have this data, that's what I'm trying to communicate, and what the transaction layer will do is it will add a header and something called digest, and that, so now this becomes what gets added by the transaction layer. So transaction layer has added header and the digest, and then the link layer will add the sequence number and LCRC, and then the physical layer will add this framing information for the start and the end, right? So this way we did it. Now when it adds the header, right, the transaction layer, when it adds the header, it adds the 16 bytes, right? So 16 bytes get added, and the bytes get, like when the transmission comes to this point, the transmission happens, this header 16 bytes get transmitted this way. So first 0th byte goes, first byte goes, second byte, third byte, each of those bytes are taken, they are like converted to serial and transmitted in that order on the PCI Express serial line, right? Say we are taking a by one just to keep it simple. So each one of them, they get taken and in that order they get transmitted. So now what that means is that when I am modeling this particular transaction, let's say I am modeling the header of the transaction layer, then in my sequence item, when I create, I need to declare all these fields, right? What are all the fields? So I will say length, I will say, you know, TD, EP, right? Attributes, then the type, format, requester ID, right? All of these, and address fields. So all of them I will just declare as fields within my transaction layer sequence item, right? So I have declared them as independent fields of appropriate width, right? So for example, this whatever the length may be, if it is 10 bits, then I will be declaring it as a 10 bits, right? So if the address, the overall thing is 64 bits, I would have declared a 64-bit address over here. So this way, whatever, depending on the different width of the different fields, I would have declared them as the properties in my sequence item class. Now, but when it has to be sent on the line, those fields have to be packed in certain order, correct? So in order to pack them is when I'm going to implement a pack function. Okay, so when I pack it, I want them to become in a particular bit vector. I want them to be arranged in this order so that I can pick them byte by byte and then send it onto the line, right? So that is called as packing. And when these bits are received, right, like let's say whatever this, I have these 4 D words, right? So when these are received, right, when all these bits are received, what I want to do is I want to again unpack them into my different fields, right? So as we had talked about, this is similar to the concept of like, packed struct or the union concept that we had seen, wherein we had the, it's more similar to a packed struct, wherein we had, like, we were able to create a bit vector if we wanted it, and then we could look at it as the fields as well, right? So that's what is the idea of the pack and unpack. So let's look at how we do it in the UVM. So we have the express transaction. Of course, I'm not going to show you this one, it will become too much of a detail, but the idea, right? So that idea remains same. It's just that the number of fields becomes more, right? We have the express transaction, we have UVM extending from the UVM sequence item. This do pack, do unpack functions become available from the UVM object, and then these are they all return void, they are returning nothing. And then what we do over here is we say do pack, and we are passing the, like, the UVM packer is what gets packed to them, is what is gets passed on to it, and then we call super.dopack. And as we had looked at, we had this bunch of field macros, right? So we look at, like, we have this tick UVM pack int. So whenever you have an int field, you tell that to your policy class through this macro, right? So, and the policy class will take it and convey it appropriately to the packer function, or you could be using the functions the way we had used it for the UVM printer. So if you have an enum, there is a tick UVM pack enum type of a macro that is available through which I can pass it. And then if I have an integer of some n bits, I can pass those and specify the number of bits present in them, right? So similarly, I have unpack macros. I am specifying tick UVM unpack int, unpack enum, unpack int n, and then I'm specifying the appropriate number. So using these macros, it can become slightly easier if you directly use functions. So sometimes you might have to figure out a little bit extra documentation and do it. But bottom line is, generally, as we have been discussing, that you can always pick something that exists and take that and then modify it, right? And then while modifying, whatever the doubts that you get, you go look up the documentation to understand it, right? So you don't write things from the scratch. Generally, that you don't do that. You take an existing example, and then if you are able to make sense out of it based on your understanding, you directly use it. And some things that you are not able to understand, you go back to documentation and reference it. That's the way to write the UVM code. And when you want to use it, right, when you want to use these functions, the way you do it is, here I am calling the default packing in terms of bits, but we can do the, like, the pack byte or a pack int. For example, if I were to do it for PCIe, I would use pack int because that's the 32-bit format that it would provide me. I can obviously do the pack byte and then extract 4 bytes every time, right? So that also is possible. There are various ways of doing things. So depending on application and depending on the requirement, you can choose the appropriate one and use it. But the idea again is simple, right? So putting everything together in the form of bits, and then those bits can be, like, I can return 8 bits at a time, which will become pack byte. If I return 32 bits at a time, it will become the pack int. And if I return everything is just the default. Return everything means return all the bits that I have created, becomes the regular pack unpack. So I am declaring an array of bits, and then I am saying I have declared the xbus transaction A, and I'm calling a.pack array of bits. So what will happen is the array of bits will be, like, it will pack it in this order, right? Whatever the order I have specified, it will pack, and it will create this, it will become 32 bits. All these fields added together, it will become a 32 bit, and those 32 bit will be returned in this unpacked array of bits. And let's say that I had a virtual interface in which I had a 32-bit bus on which I wanted to transmit it. I can use the streaming operator and pass this unpacked array of bits, and it will convert it to, the logic 31:0 type of a format. and then I can just assign it directly to the 32-bit bus that is present in the virtual interface. Similarly, if I want to unpack it, and let's say I'm receiving it from a bus which is of the type, like, logic is a packed array, I can take it and then I can put it into unpacked array of bits. Typically, as we know, in the test bench we always operate on the unpacked arrays because of the flexibility that they provide. And then we have an unpacking operator over here. This 32-bit from the logic is getting converted into unpacked array of 32 bits, and that unpacked array, when I pass it to a.unpack, what it will do is it will take those 32 bits and then distribute it back to these particular fields that I have with the appropriate size. And yeah, so that's the way the unpack works. And the individual field values, when I access, I'll be able to see their individual values, right? So that is what is the unpacking, taking all the bits, and it knows from which position to which position is address. So it will take that and put it into the address from the next bit position to next bit position, which is a bit position for the TR type. It will take it and put it. So it is similar to this, right? So this bit position, it will take it and put it into length. I mean, let's say I'm just making it up, put it into address, and the next field is, let's say, TR type. It will put it into TR type. From here to here, let's say it is size, I'm going to put it into the size. So because while specifying the pack or unpack, we have specified the field and the field widths, right? So based on that, from the array it knows from what index to what index it needs to pick for each of the fields. It takes those values and puts it into the corresponding variables, and now the transaction can consume those variables. For example, after unpacking, I could send it for comparison, right? I could have stored a reference transaction somewhere, right? And then now, after, let's say, from the serial line, I have received it, I have taken it into those group of bits, and then I have unpacked into my transaction properties, and then I can send it for the comparison, and then both the properties of the two different objects can be compared, and we can check whether they are matching or there is a mismatch, right? So this is the way you use pack unpack depending on your application requirement.